Okay, our next presenter is Helmut Simonis, and Helmut is a senior researcher at the Insight Center of Data Analytics in Cork, Ireland. And Helmut concentrates on a combination of machine learning and optimizations using different technologies. In particular, he is an expert in constraint programming, to which he devoted a lot of time and years of his life, being author of one of the famous constraint solver. And Helmut used to be the president of the Association for Constraint Programming, and currently he's concentrating before generative AI came. He spends a lot of time on automatically learning constraint models. Like we're trying to learn decision models, but he's learning constraint models for quite a long time with very interesting results. And to keep it brief, I would, because I know Helmut personally, I was happy to work with him door to door for 5 years. And I would tell you, if you ever have very complex optimization problem, Helmut is a person to approach. You will get good advice. Helmut, go ahead.
Okay. Thank you very much for the kind introduction. Yeah, so this is a slightly different talk. This is a solution to the Roadef challenge. And if you don't know what the Roadef challenge is, then you'll learn about that. So it's something completely different. This is about constraint programming and optimization for decision support. So it's artificial intelligence, but it's declarative AI, as we have also heard this morning. It's not statistical AI. And on the other hand, it's not rule-based at all. This is constraint-based. And this work is done with a group of PhD students as a side activity because we didn't have enough on our calendars to work with. If you haven't heard about the Insight Center, then here's a little overview. It's a national center of Science Foundation Ireland with a number of universities being the main partners, and UCC, University College Cork, is one of the main partners. But a number of other universities involved, basically all universities in Ireland are involved at this point. Nationally, we have something like 450 researchers, 150 million funding, and yeah, you see here a few thousand papers as part of the center. So it's quite a large activity focused on data analytics. In Cork, we are doing decision support, we are doing constraint programming and optimization. Okay, so what is this talk about? This is all about the participation in the French OR Society competition, the Roadef Challenge. And it's a kind of hobby project driven by a group of PhD students. And our aim was to achieve good results with limited effort and relatively low risk approach. We didn't want to go for the blue sky kind of activity, which may or may not work. We wanted to have something which produces a result relatively quickly. We use optimization and constraint programming where this is possible. And we had kind of mixed results. We were fourth in the qualification phase and eighth in the main evaluation out of 52 teams. So this is not bad, but we probably could do better if we put a bit more effort in. There are two more stages of the challenge to come. So perhaps there is time for further improvement. So what is this Roadef challenge? The Roadef Challenge is a competition which is run by the French OR Society, Roadef, since 1999. And since 2010, it's in cooperation with the European Operational Research Society. And it runs every 2 years, and every 2 years there's a different topic. It's a multi-stage competition with open and hidden data sets. So you are evaluated against unseen data as part of the competition. The problem typically is provided by an industrial partner, and in 22 it was Renault. And typically these problems are very close to industrial reality. Sometimes perhaps a bit too close because you have to understand all the side constraints that might occur. Here's a list of the past challenges. Okay, I'm not going to go through all this in detail, but what you can see is it's a wide variety of different problems, from energy management to satellite mission planning to cutting class. And if you look at the companies that were sponsoring these things, you see that basically all the large French companies are involved in some form. Okay, the 22 problem, as I said, from Renault, it's about the transport of items to make cars from suppliers to the factories using semi-trucks, articulated trucks or semis or whatever you want to call them. So a truck and a trailer which carries the items. And it's a problem over a period of several months, the planning. You cannot deliver the items late, but you can actually deliver them early. And every factory, this is the global network, is one instance, and we have 20 to 50 instances per data set. The items are placed in crates, which can be stacked, and we'll see that in a picture in a moment. Different types of trucks, short ones, large ones. So you have sometimes choices which trucks to use. You have a calendar of planned trucks which are given. So these are trucks that will make a journey at a particular time, and you can use them or you may not use them. And if you need more trucks, you can make copies of these planned trucks and say, I want to have 2 trucks rather than 1 if I need that. The overall cost is the cost of all the trucks that is used, plus the inventory cost of the items that are delivered early. So it's not quite a transportation problem because we're abstracting the locations and the distances, but it's in this area. So what are the main concepts? Well, we have the concept of an item, which is basically a piece of or a component of a car. This typically specifies that you want to transport a certain number of them. If we break that down into the individual pieces, the individual copies, this is something that we need for the output so that we can say this will be placed in XYZ coordinate in a particular trailer. We have the planned trucks, which are the trucks that are given in the calendar. And then we have some form of compatibility data, which says whether an item can be in a particular truck or not. What you do with the pieces is you actually stack them in so-called stacks, which you can put into an actual truck. And an actual truck is one of the planned trucks or a copy of that. And you also have some parameters. Now, the compatibility stuff is much more complicated. I'm not going to talk about that in details. You have some temporal constraints saying that every item has an earliest and a latest arrival window, and you cannot deliver things late. So it has to be in the factory by the latest arrival time, and it cannot be in the factory earlier than the earliest window. And in between, you can choose whatever time you want, but you may have to pay an inventory cost if you are multiple days early. Typically, the latest time point corresponds to some planned truck, so it's always possible to deliver things as late as possible. You can't be late even on the same day, and if you are early, then you have to pay an inventory cost for every day that you're early. So that cost varies a lot dependent on the size and the properties of the item. But you don't have any cost if you deliver on the same day, but earlier on the same day with a different truck. So it's a 3D placement problem. You have well, a 4D placement problem. The 4th dimension would be which truck to use. But for one particular trailer, you have these stacks of items that you can put in the truck so that they fit within the truck, obviously, and they don't overlap. You can put pieces only in the given orientation in the set direction, so you cannot actually rotate them 90 degrees or turn them over, but you can actually rotate them on the X and Y plane and put them lengthwise or widthwise, as this is called. You can only put things in a stack if they have the same footprint and if they are compatible. Obviously, everything has to fit within the trailer volume, and all the weight of all the pieces must be below the capacity of the trailer. So that is not too complicated, but there are more constraints coming up. The first one is that you need support in Z and X direction. So Z is going up and X is going from front to back. In the Z direction, obviously, you can only put something either on the floor or on top of something else. If you put it on top of something else, then it has to have the same footprint and orientation. The crates actually connect together, so you actually have to stack these things properly. You can't have items float around in space. Or you can't place them like in a DHL truck, just parcels on top of each other. That's not allowed. And in the X direction, you have to have either an item at the front of the trailer. The front is here on the left side. Or it has to have another item immediately to the left. So this green item here is supported by that green item, which is supported by the front. That item here is not supported by anything. If you brake, it would actually shift, and that's not allowed. The definition is a little bit weak in that this is a feasible supported item, although you only have very limited overlap here between the item with the question mark and the item to the left. This is still allowed. So some of the rules you may want to refine for a really practical solution. You can stack crates in these stacks, and you have to understand that sometimes you actually gain a little bit of space. So you can only stack crates if they have the same footprint, the same length and height, length and width. If you actually put them on top of each other, the little bars here are locked together, and therefore you gain a little bit of space. So the total height of a stack may be less than the total height of the items themselves. You can only place things either lengthwise or widthwise. So with this rotation of 90 degrees, you can't actually put them at the angle of 60 degrees just because you might pack another item there. It's not allowed. Some of the items have fixed orientation because you only want to transport them in a certain way so that you don't get any damage of the items. Okay, then you have constraints about the loading order. So the trucks bring the stuff from the suppliers to the factories, and the truck may be visiting multiple suppliers. And the rule is that you have to put the things of the first supplier that you visit to the left, to the front of the trailer, and then the second one, the third one, and the fourth one. The rules actually are more complicated than that, but that gives you an indication. So you cannot actually put these items here at the very end of the truck because you like them better there, or they would fit better in this particular place. They have to be at the very front, and that puts a lot of constraints on the placement. And then there are more complicated things. This is a diagram from the challenge description. I'm not going to explain this in detail, but you have the pin where the trailer connects to the actual truck. And you have to make sure that you are not putting too much weight on this pin and in particular on this mid-axle of the truck. So these are non-linear constraints. The more items you put to the left, the heavier that part of the truck gets. But if you put something here at the very end of the truck, it acts as a fulcrum, and you actually reduce the mid-axle weight that way. So it's not incremental. Adding more items can actually reduce the axle weight in a rather bizarre way. You have to make sure that you are satisfying these constraints for every supplier individually. because you are actually traveling from each supplier to the next, and it has to be safe at every time you are on the road. So this is quite a complex set of constraints. Fortunately, there is a checker provided, and it will reject the solution if you have too much weight on any of the axles or any of the other constraints that are imposed. The instance parameters, we have some parameter about the relative cost of transport versus inventory. And in the data sets, we have ratios of 1:5, 1:1, or 5:1. So you are getting a very different impact of the inventory cost in these different scenarios. You have a cost increment if you use extra trucks. And that means that you are better off using the trucks that are already planned. But you don't have to use all of the planned trucks. Then if you don't use them, you are not paying for them. But if you use extra trucks, you have to pay more than a normal truck. And you have between half an hour and an hour for each of the instances. So what's provided? There is a problem description as a PDF. There are the competition rules as a PDF. There are the instance files, multiple files per factory. It's a French CSV format, which is the first time I actually saw that. So it's not comma separated because the comma is used as the decimal separator in the French format as well. So you need to do a little bit of, at least for an Irish person, you need to do a little bit of work to read the data. There's the result checker, which is a Java program, which decides if a solution is correct and what the cost is if it is correct. It provides some cryptic information about what is wrong if something is wrong, but you'll have to interpret that very carefully. And there is a 3D visualizer, also in Java, provided, but we didn't use that because we did our own visualization. How's the competition run? Well, the competitors provide binary versions of their programs to the organizers, and these programs are run on Roadef machines against either known or unseen instances. The competition machines only have certain commercial tools installed. So if you are using a particular solver, it may not be installed, and so you can't actually use that. And you have limited resources, number of CPUs, number of memory, and about time. The solutions are checked with the checker, so you would have an understanding of that because you have the checker yourself available as well. And then you get points for every instance that you solve compared to the solutions provided by the other competitors. If you are better than another competitor, you get a point. If another competitor is better than you, they get a point. And then you have a total ranking, which is based on the sum of the points achieved. I should say that this is the way that a lot of competition in the optimization area are run. So this is quite normal. But okay, in this particular case, there are two things I wanted to point out. The problem size does not matter. So there are very large instances and quite small instances, but you only get 1 point if you are better on the big instance, and you get 1 point if you're better on the very small instance. And obviously, you need a lot more trucks for the large instances. So you could also make a ranking based on the total cost, but they decided not to do that. I think for continuity reasons, because in previous years, it was always based on this point system. Now, one thing which is quite tricky is that it runs over multiple stages, but you never know what the other solutions look like. You only know what is the best cost value for every instance that was found so far. And that's made available at the end of each phase. So you can see where how you compare to the best overall solution, but you don't see what the best solution is, nor do you know which other team has that best solution. Okay, the challenge was run starting in July 22. There was a sprint for early participants with the dataset A in October. We did not attend. We haven't even started at that point. We only started end of October. There was a qualification phase with the dataset B in January, a test phase with dataset C and X. X was the unknown, unseen dataset in June. For some reasons, people were not happy with this test evaluation. There is another stage coming up end of September, again for datasets C and X, where you have unlimited evaluation. And then there's a stage where people describe their scientific contribution. So at the moment, I don't know what the other teams actually have been doing. I know what results they obtained, but I can't tell you what other methods they have been using. So it's perhaps a bit early for this type of presentation. Okay, what's important to understand is that the early data sets are quite different from the later ones. The number of items and the number of trucks are relatively small in the beginning, and the trucks are spaced in the calendar. So it's much more difficult to do early delivery. If there's only one truck per week, then if you deliver early, you have to have a large time window and you have to pay a high penalty. The daily inventory cost is quite high, and not all of the constraints that are specified were actually present in the data. So I think this is done on purpose with the Roadef challenge to lull you into complacency that, oh yeah, we can solve data set A, but it's very challenging to develop a tool based on the early instances that performs well on the later ones, because there will be constraints that you have never seen before. They were specified in some form, but they were not present in the data, and the scale of the problem changes quite dramatically. So it's difficult to develop this. It's easy to focus on just improving the instances that you already know about, and you don't really know how good your solution needs to be. Because you don't know how the other teams are doing for the current data set and the future data sets. Here's an example of some of the data here of some of the instances from the dataset X. So what we have is something like 200,000 pieces that we need to transport, 10,000 trucks, 300 suppliers, 2,000 different products in each instance. And altogether, we have a few million pieces to transport, 150,000, 200,000 trucks to worry about. Well, truck trips, I should say, not individual trucks. And you also see that you have different parameter combinations for more or less the same data set to test out how your system works with inventory or no inventory. Okay, now our approach. How did we get involved? Well, a group of 4 PhD students wanted to participate in this challenge. A little bit of background. We came second in the 2012 challenge. This was by Google about data center reallocation. I was a part of that team as well. So they said, okay, yeah, we want to actually try and do this. And they involved some of their supervisors. And then they asked me to help with the overall design at the end of 22. So what we did was organize weekly meetings, either remote or in person, to discuss progress. And we use our Java development framework, which is a code generator for a lot of the boilerplate code that you need for these optimization problems. And it has visualization and reporting tools. I've used it for something like 50 different projects so far. So it's quite a well understood framework that scales to the required scale with ease. So what are the aims? Well, it's a complex problem, and it's not at all obvious how to find feasible solutions. You have instances which are quite small, but also some which are very large, and you don't have a lot of time. 1 hour sounds like a lot of time, but if you have 10,000 trucks to worry about, it's not a lot of time. And our first aim was to find feasible solutions and then try and improve the solution quality. And the only way we really thought we can achieve this is by decomposition. Either decompose the problem into really separate independent subproblems, which is very nice if we can do that, or create a sequence of subproblems that chain together and where you use the output of one subproblem as the input of the next one. And this way you are creating much more manageable subproblems that you can build independently and where you have a much higher chance of finding a feasible solution. But of course, unless you do something really clever, this decomposition, especially in the sequence of subproblems, will not necessarily find the optimal solution. We try to avoid a high risk, high reward approach. So you could try and solve this whole thing as one optimization problem and come up with a really clever technique on how to do that. But okay, if you have only limited amount of time, then this is really taking a high risk. We wanted to make sure that we at least qualify for the final stage. And obviously, because we have so many little subproblems to solve, you can't afford to spend a lot of time in any of the subproblems. So as a first step, we defined a minimal viable product where we place every item on the last possible truck. So that creates independent subproblems for each planned truck. All the items that can be delivered on that truck will actually be transported by that truck. We create a minimal number of stacks of compatible items. So this is a version of a bin packing problem. And then we place all the stacks that we have created in the truck. That is now a 2D placement problem because we deal with stacks and not the items themselves. But we may need more than one truck to take all the items. Now, in this approach, where we take the last possible truck, we don't have any inventory cost. Everything is delivered just in time. Then we only have to produce the result files, check against the checker, and see whether our solution is okay. And that validates our understanding of the problem and provides a baseline for later things. So we decided that is the first thing that we're going to do. Now, we are building the stacks. We actually wrote an optimization model for that, but we can't afford to run the optimization model. We have a few 10,000 stacks to build. This wouldn't actually fit in the available time. So we use a heuristic solution for the stack building, where we put together things with the same footprint and load stage. Here we have a visualization of the stacks. So this is the height of the truck. And you see that for some of the things we are using basically all the available height. We have here the gain of the nesting, where we are pushing crates together. And here we're actually not able to put a fourth item here because we have a constraint saying that you can stack at most 3 items of this type together. Yeah, this is the output of the stack building. We have these individual stacks now, which have their footprint. We can check against the lower bound to see whether we are optimal, and we're optimal in something like 92% of all the cases, and typically just one off in cases where we are not reaching the lower bound, and quite likely the lower bound is at fault rather than the heuristic solution. Okay, then the placement, and initially we thought, well, this is good stuff. We know how to do 2D placement because we have done a lot of work using constraint programming for placement problems. Here's an example from an earlier paper that Barry and myself wrote for CPIOR in 2011 on almost square packing. That was an open problem at the time. So yeah, we're doing quite well with this, but we decided not to use that technique in this case, because we have a few thousand sub-problems, well, one for every truck that we're using. It needs too much time to run these optimization problems for every truck. And it requires tools that are not installed on the Roadef machines. And we were not willing to fight Roadef on getting these tools installed. The axle weight constraints would need some new constraint formulation, and that would be a high risk approach. And the support of items on the X direction is also only handled by a few of the systems. So instead, we built a placement heuristic. That's basically a version of the constraint-based model, which doesn't backtrack. So whenever you place an item, you are committed to that item. And you see here the items. This is the footprint of the trailer. You see the items with the earlier load stage here on the left, then the second one, the third, and the fourth. And in this case, they all fit within this truck. You could argue that this is not a beautiful placement, but there are no extra points if you have a beautiful placement. So if everything fits then and satisfies the rules, it's okay. We have here the axle weight. We're at 11.3 tons with a limit of 12. So we're still well below the limit. And we can again use lower bounds to check optimality and see whether we have made a good solution with our heuristic. Now, once we had done that, we saw that we were not particularly good in terms of quality of the results. So we tried to make some improvements. The first thing was to add a portfolio of placement methods so that we have more chances of finding good placements. And then we needed some counterfactual explanations. I'll talk about that in a moment. And then as a last extension, we allowed stacks to be transported earlier, not necessarily at their latest time. And for that, you need to do some clustering of the trucks and allow movement of the stacks to earlier trucks and trade basically the number of trucks that you need against the inventory cost that you incur. Okay, placement portfolio. The heuristic that we have is very fast, but it's incomplete. But we can afford, this runs in milliseconds, so we can afford to make many runs. So we have a number of variations of this heuristic. And on the right here, we have basically a table which has all these variations here on the left and the different instances of a particular data set as the columns. And the number basically says how often each of those heuristic actually fires and produces a valid solution. And you see that we're using a lot of different variations, and this improves the solution quality quite a lot. We also tried to run some complete models, some optimization models for special cases, and we add some fallback heuristics to always find a solution, because if you don't find a place for some item, then your solution is invalid, and everybody else basically gets a point from you, and this is very bad. So it's much better to have a bad solution rather than no solution at all. And then we need some explanations, because we were looking at the solutions and sometimes we would say, why did you do that? And why didn't you do something else? So here we have a solution at the top where we use 2 trucks. And we see there is some space in the truck on the left, and you only have a small item here. It would be easy, a human would say, to take that item and put it somewhere else, for example, in this space here. So why didn't you do that? And now the system basically needs to explain that, yeah, I tried that and it didn't work. And it provides these counterfactual explanations. And I tried this, which is actually a nice placement, which uses only 1 truck, but it exceeds the axle weight constraint. And it has a few more of these counterfactuals, which are even worse in terms of the axle weight. So this is good for a human to understand yeah, this is not something where the system did not consider displacement at all. It did consider it, but it didn't work for one of the constraints that needs to be satisfied. So that's very useful when you actually look at the results to distinguish between the cases where there's something missing in our solution and something where it's just like that. And you end up with this nearly empty truck. And you have to do something else. You basically have to take that item and put it into an earlier truck to get rid of this truck. And then we have the preprocessing for the clustering, where we basically see which of the trucks can interact with each other, and only a few of them basically can interact because the trucks are not necessarily visiting the suppliers in the same sequence. And not visiting the same suppliers at all, it's not always clear whether two trucks can interact. But if an item can actually be placed on either of two trucks, then you have to take them together and you have to solve them in one go. And then we are finding connected components in the generated graph to find the clusters that we need to worry about. And then for the movements, so this is what we do when we have an initial solution. So what we have here, we have the trucks in time, and sometimes we use two trucks rather than just one. And now what we're trying is, can we get rid of these trucks and basically transport the items that were on this truck in an earlier truck? And the arrow basically say which truck we have selected. Now, we do this by a little optimization program where we try out all possible combination of all possible movements, and then we try the movement that is maximizing the benefit, because some of the movements interact with each other. It doesn't make sense to move something from this truck to that truck when you have already taken everything that was in that truck and moved it earlier. So there is possible interaction there of movement that you want to minimize and that you want to still, where you still want to maximize the overall profit. So that was this movement solver. And just for fun, here's the object model of the system in December. We did a code review at that point. Not all attributes are shown, obviously, but you see it's not that complicated as applications go. But yeah, there is quite a few concepts, quite a few things that you have to worry about. After the qualification phase, we actually did a redesign and looked at what was happening with the next data set, and we basically did make a generalization of our solver here, where we're saying we are not just taking items and place them as late as possible. We try and to place them whenever they can be placed in such a way that we fill up the trucks nicely and we minimize the inventory cost that is created. Now, at that point, we haven't solved the placement problem, so it's maybe optimistic, and we may end up with multiple trucks when we actually plan to have only one. But this is a very useful thing when we have, like in this case here, now multiple trucks on the same day. So there's one here at 1:35, at 5:35, and at 9:05 in the evening. And you can move items that were planned on this truck into an earlier one. You can't go back, you can't go to a later truck, but you can go forward. And you can try and minimize the inventory cost that you incur. If you're on the same day, you actually don't have to pay any inventory. Okay. We also have an optimization where we can pre-compute some types of solutions where certain truck sizes and item sizes occur very frequently. You can think of these things as Euro pellets, basically in metal, but they are the sizes of Euro pellets, and quite a lot of the transport is done on those. So you can then build basically pre-computed solutions which maximize the utilization, provide support, and push most of the weight to the right of the truck, minimizing the axle weight constraint that we have. So we can pre-compute that and then use that at runtime just to look up solutions. As you have seen, there's a lot of visualization going on because we can only really understand the results by visualizing them. If you just look at the numbers, there's nothing you can understand. But you have to avoid information overload, only show what is needed. And that depends obviously on the situation and the user. So there were lots of details on these plots that I've shown that you didn't understand and I didn't talk about, but they were actually useful for certain analysis. We're using a library of predefined visualizations of our framework in Java, but also we have developed quite a few custom visualizations for this application. It produces LaTeX because we are at the university and we like to write papers and do our slide presentations in LaTeX. So this is quite useful for us. Okay, a little bit on results, just to give an indication of what the overall code size is. As I said, we are using our application framework, and that application framework produces something like 115,000 lines of code generated from something like 1,000 lines of model specification. Then we have I/O, let's say 2,000 lines for import and export. The overall solvers, quite declarative, that takes something like 6,000 lines, and the visualization is another 4,300 lines. So altogether, the handwritten code is 12,000, 13,000 lines of code for this. So it's still a manageable piece of Java code. Here we have a visualization of the example result quality. So what we have is every dot is one truck in one instance, it's the instance CI from dataset X. So you see there are quite a few trucks in this particular instance, and the truck is placed based on the area utilization and the weight utilization. So ideally, we want to have a truck here which uses nearly 100% of the area and 100% of the available weight. But yeah, we have a lot of trucks which are area limited. We are close to 100% in the area utilization, but the items are not particularly heavy. And nothing we can do about that really. We also have the color here, which is showing how close we are to the mid-axle weight. So 100% is the capacity limit. If it's in red, then we are 90% plus. So even for some of the very sparsely loaded trucks, we are hitting these axle weights at some point because we have one item which is quite heavy and which has to be on the left of the truck, and we can't put anything more in there because we're hitting that axle weight. So anything which is here in the lower left corner is bad, and we're not using these trucks very well. And anything which is here at the top and to the right is good. So we are doing okay. We still have to work on these cases where we are not doing well, and that is some future work. But for the majority of cases, we're doing well. This is another plot where we compare against the other participants. And what we have here is the objective value, the overall cost of the solution, and the gap of our solution to the best solution known. Yeah, for very small instances, we are basically at cost zero, but also we are finding the optimal solution. But even for small instances, we have cases where we're not doing very well. What is encouraging is that as we actually increase the problem sizes and make the instances bigger, so more trucks, more items, we are getting better compared to the other solutions. We are basically not at the top, but number 3 or 4 and we're 5%, 6%, 7% off the best solution, which is also quite close to the lower bound that we calculate. Okay, now the results are one thing, the student experience is something else. So we had a roundtable discussion with the students as part of our training course to tell people about this. The students said that this was a very valuable learning experience because they have never actually learned how to approach a large-scale problem and how to use visualization to understand things at this scale, and how to understand the effort and reward compromises that you can make. And they also said it was lots of fun and was nice to work in a team rather than just as a single PhD student. So I think from that side, it was a full success. Overall, I presented some results for our entry to the Roadef challenge, driven by the students with limited time available. It's a very challenging problem, both in complexity and scale. We are using decompositions to create manageable subproblems that we can solve with optimization. I would say fair to middle in terms of results. I had hoped to do better, but okay, with the time given, I think we're doing fairly well. And some stages are still ongoing, so perhaps we are going to get still further improvement. And I think that is it, yeah.
Oh, okay, thank you, Helmut. We do have similar questions from me and from David about, because most of us always concerned when we make decisions about explanations, and you mentioned your counterfactual explanations and how you keep track of them, and or did you answer this afterwards? That's there are two same questions here.
Yeah, so this is a research area that we are working on in Cork in a much larger context. Now, explainable AI is a big thing, but constraint programming in particular is by its design explainable because it's logic-based and you can actually understand the reasoning that is applied. So here we are basically recording solutions that are better than the selected solution in some aspect, but do not satisfy all the constraints. And we present that as alternatives to the user so that they can see that, you did actually explore that, but it doesn't work because of this particular constraint. And that is a very useful thing to make sure that we are not leaving out certain possible solutions, but we're actually exploring them, but we have to reject them because some of the constraints basically are not compatible with that.
There are concerns about memory. Do you keep all of this explanation all the time, or you let people ask questions afterwards and produce these explanations?
In this particular case, we're actually we're recording all the solutions that we have ever considered.
So that's a huge memory you need.
My machine has 128 gigabytes of memory. It's not a problem really. Even if you have even if the visualization and all the details about the solutions, you can store that in a relatively compact form. It's just that you have to spend that memory. Okay, fine. We don't have so much time to actually produce a lot of alternatives. We are not creating millions of solutions. We are creating hundreds of solutions for every truck.
Yeah. More questions? Please just unmute yourself and ask question because it's really interesting. This is not just theoretical or application or for competition. It's very close to real life. because many years ago, for example, I was intimately involved in similar problem when we did this for truck loading and routing problems, and we were very successful for small kind of problems when you had 50 trucks, and if you saved even 3 trucks, it's a huge saving. And Thomson, I forgot, Thomson logistic company, they use this and they saw this effect, and it was our product was quickly bought by a larger company, and they use constraint programming. But I remember that one of the challenge was how to minimize total number of trucks, but you have even more challenges. And I hope you did not try, let's try 5 trucks and 6 trucks. You did something smarter, right? Can you just a little bit tell here?
Well, okay, here the point is you have an optimization model that basically says I have all these possible time points when trucks can travel. How do I distribute my items over all these trucks? And how many extra copies do I allow? And then solve that as basically as a MIP. And well, not to optimality, but very close to optimality. 0.1% optimality gap is our cutoff point. So for a case where we have a few thousand trucks in one cluster, yeah, this is it's quite successful. Now the challenge afterwards is can you actually pack all the items into those trucks? You have made sure that you have enough weight and you have enough area to take things, but can you actually find the placement? And if that is not possible, then you incur some extra trucks that you have to get rid of afterwards again. So that's another step of the solver. And you could actually do some form of Bender's decomposition. In this case, it's a typical master subproblem kind of situation. But given half an hour time, this is not manageable. If we have 24 hours time, we could do that. But for the competition, that was simply out of reach.
Yeah, that's certainly a problem, and I know that you also need to avoid so-called widow trucks when you have just one little item and you need the entire truck to deliver this. So you need some preliminary evaluation of all trucks, and you want to, even if you have this truck is optimally loaded, but you want to save some loads, some pallets and the products for other trucks, not to keep them simple. It's something similar what Donald Knuth said when he avoiding empty pages when he builds documents, something similar, and we use this technique also. But we have one more question from David. You can see it.
Okay, yes, the counterfactuals are basically also used to validate our lower bounds. This is an important aspect when we actually try and place the items. We estimate how many trucks we will need, and sometimes, well, most of the time we'll deal with a single truck, but sometimes we need 3, 4, 5. And then it's very useful to know that we will actually need 3, or that yes, you can try with, or you can place things with 3, but then some other constraint will not work. And so the counterfactuals basically also validate the lower bounds for us. And the whole lower bound calculation is a bit technical. I left out most of the details there, but there's fun stuff to be done there as well. And we have a lower bound calculation for the overall problem, where we can actually see what is theoretically possible with this whole approach. So that is a nice scientific contribution. I think nobody else had that so far.
Okay, probably we don't have time for more complex questions about Bender's decomposition and more. And this is from our next presenter, Ryan, who will also talk not only about loading, but a combination of loading and routing probably. So all these problems really could be discussed by hours. So Ryan, sorry, we can put it aside, your question, and Helmut has, you have Helmut's email, and you can address this question directly. Helmut, thank you very much for very practical application, and you open a lot of things. And if possible, can you send link when you have this final solution published or anything we can read more?
Sure, yeah. So the idea is that beginning of November, there is a submission of documents describing the different approaches. Typically, once you read what the other guys are doing, you find, oh, I could do that as well. And suddenly everybody has a big improvement in their solutions just by picking up some of the simple ideas of the other people. So this happened with these Roadef challenges all the time. So there's a bit of ongoing work.
I see. But whenever you want to share your results or other people's results, send them to me, and we will publish them on DM community as a continuation of your work.
Right.
And again, thank you very much for your presentation.
Okay.
And we will move forward.